at 0, 0. Okay, so I know my x-intercepts, I know my y-intercepts. I'm now interested in my turning points or my stationary points. So stationary points occur, remember, at y dashed equals 0. Okay, so now I need to find my derivative, and y dashed is equal to 4x cubed minus 12x squared. Okay, so now we're going to put y dashed equals 0. So 4x cubed minus 12x squared equals 0. And again, I can factorize this. So I can take out a common 4x squared, and I'm left with x minus 3 equals 0. And again, using our null factor law, I get that x equals 0 or x equals 3. Now, I know something's happening at x equals 0 and at x equals 3. I don't know what yet. Okay, now I need to find out what the nature is of my stationary points, and I can use my second derivative test, or I can use my table to check what's happening. Let's try using both here. So use second derivative test for the nature of my stationary points. And let's have a look. Our y double dashed is equal to 12x squared minus 24x. And I'm wanting to know what's happening at x equals 0 and x equals 3. So at x equals 0, y double dashed is going to be 12 minus 0. It's going to be 0. Okay, and remember, when that's equal to 0, we actually need to confirm what's happening. We can't just use our double derivative test. So we'll confirm that in a minute. At x equals 3, y double dashed is going to be 12 times 3 squared minus 24 times 3. And that gives me positive 36. And y double dash greater than 0 means that it is concave up, and I have a minimum turning point. Turning point. I don't know what that turning point is. I need to find the value. So let me just fix that in. Remember, I've only got an x value. So when x equals 3, our original function f of 3 is equal to 3 to the 4 minus 4 times 3 cubed, and that gives me negative 27. So I therefore have a point, a concave up or minimum turning point at 36, negative 27. Okay, let's have a look what's happening with this at x equals 0. And we're wanting to have a look at our first derivative. So we've got x and we've got f dashed of x. And we're looking just before and just after. So negative 1 and 1 be fine. And f dashed of x, so my derivative of x at x equals negative 1 would give me negative 4 take 12, which is negative 16. So it's going to be less than 0. And so my graph's doing that. At f dashed of x equal to 0, we know it's 0. And at 1, I'm going to have 4 times 1 minus 12, because gives me negative 8, and that's also negative, less than 0. And I have a point of inflection, or a horizontal point of inflection, on a falling curve. And this is at the point 0, 0. All right. Now, we found our stationary points. We've got a horizontal point of inflection here at 0, 0, and it's going to disappear. So 0, 0. I also have an x-intercept here at 4, 0. And I know I have a minimum turning point at 3, negative 27. 3, 22, something there. Okay. That's it. At 3, negative 27. So far, this is what I know about my graph. I'm now interested in other points of inflection. Okay. And remember, that is when my second derivative is equal to 0 and there's a change in concavity. So for other points of inflection, I need f double dashed of x equals to 0. And that means that 12x squared minus 24x must equal to 0. So that means that 12x, and I can factorize it. So using my null factor law, I get that x is equal to 0 or x equals 2. Now I already know there's a point of inflection at x equals 0, so I know what's happening there. But I need to find out what's happening at x equals 2. And remember, I need to show that there's a change in concavity. And I'm interested in my second derivative, so my values of x and what my second derivative is doing. And I'm going to look just before and just after, so at 1 and at 3. And when x is equal to 1, my second derivative is going to be less than 0. When it's equal to 2, it's 0. And when it is equal to 3, it is greater than 0. So therefore, there is a change in concavity and a point of inflection at x equals 2. We now need to find our y value for that point, because it's not a point until we've got a y value. So when x equals 2, f of 2 gives me, it's our original formula, our original equation, 2 to the 4. It's a horrible 4. So 2 to the power of 4 minus 4 times 2 cubed gives me negative 16. So I've got a point of inflection happening at 2, negative 16. Okay, we're making progress. Let's put that in on our graph. Okay, so at 2, negative 16, I have a point of inflection. And now all I need to do is see what's happening. So as x tends towards positive infinity, I'm going to have a positive to the power of 4, which will be positive, minus 4 times a positive cube, but the positive to the power of 4 takes precedence. So y also tends to positive infinity. And as x tends towards negative infinity, I'm going to have a big negative number to the power of 4, which will be a big positive number, subtracting another big negative number to the power of 3, which is a negative number. So I'm adding, and y will be tending to positive infinity. Okay, so that means that I'm expecting my graph to be going positive up here and positive up over here. Okay, let's draw this graph and see if we can make it look like something. Okay, be gentle. It's not easy with this machine to draw these graphs. Okay, so we're expecting a point of inflection at 0, 0, and it's on a falling curve, so we know that it's going down. My computer's taking strain. Just need to get this whole thing up on here. Needs to go down one more. It doesn't jump. Okay, no, it's jumped again. Sorry. Your patience is amazing. All right. There we go. I've got it. So now what we're going to be doing is we are expecting a point of inflection happening here. So I've got a falling curve and I have a point of inflection. And then I need to go, oh goodness, I need to go through that other point of inflection. Oh, good. Okay. I need to go through there, and I have a minimum turning point over here at 3, negative 27, and then I'm going up again to go through my x-intercept and to positive infinity.